Okay, in this video we're going to go over informed search. And this is going to contrast with what we've seen so far, which is uninformed search. So let's quickly review. So think about the search framework. The search framework that we've studied so far and is going to pretty much um, encompass all of the types of search we're going to study starts with the concept of there being a state space. Okay, and the goal is to get to a goal state, or to start from an initial state and to get to a goal state. And you do this by taking actions that take you through transitions from state to state. And each time you take one of these actions, what you're doing is you're going to expand these states. Okay, and there's a general algorithm, and let me just show you this algorithm again. So this is the tree search algorithm that we looked at in the last video. It comes out of the textbook, where the idea is you're going to maintain a frontier, right? So you initialize a frontier by putting the initial state into it, and then you iteratively grab a state out of the frontier. You check if it's a solution, and if it's not a solution, you expand it, and you take any of the new states that you discover and put them into the frontier. Okay, and if you manage your frontier by taking a first in first out policy, you get breadth first search, or if you do a last in first out policy, you get depth first search. And then there's the various there's the other variants that we talked about as well. Okay, so it's actually important at this point to then look at another variation on the tree search, which is in the textbook. So you probably already read about this, but it's good to go over it in the videos and in the lectures as well. So this is a tree search, and the other form of search is the graph search, which I've written up here, and I've highlighted the differences in red. Right, so really we just add these three lines. It's not even, one of them is not even a full line of code, of pseudocode, to the logic of tree search to make it into graph search. And the general concept is that when you're dealing with a search space that is tree structured, you can pretty much keep moving forward, right? You start at the initial state, and you generally conceptualize this as being at the top of the tree or the root of the tree, and you just move down. You can just move to the next level and not have to worry about issues like getting stuck in loops, or repeating a state, or adding a state more than once to the frontier. And these are the things that we try to correct with graph search. So if you think just popping up a level, just thinking about the applications we'd use these for, um, usually a tree search is something where it's very sequential. There's a time, um, there's kind of a time component. So there's a notion of not being able to take back one of your moves, or take back an action, right? But in graph search, or rather, we would want to use graph search in settings where we can take moves back. So if we're a robot, trying to explore the surface of Mars, it is completely conceivable that you would accidentally find yourself walking around in a circle over and over again. And that conceptualizes what can go wrong if you use tree search instead of graph search. Okay, so and how do we correct that? Well, what we do is we basically say, let's try to remember every place we visit, so if we don't visit it again, right, when we get back around. So that's what the red lines do, right? So now we're not just maintaining a frontier, but we're also maintaining this explored set, right? And then the inner loop is exactly the same as tree search. You take a node from the frontier, and then you check if it's a goal state, right? In which case you've won the game, and you can finish, you can return the solution. And then what you do is you add the node to the explored set. So you mark that you visited that state. Okay, and then after you've added it to the explored set, you then expand the chosen node, and you find all the states you can reach from the new node, the current node, and you add them to the frontier only if they're not already in the frontier, or they're not in the and they're not in the explored set, right? If they're in the explored set, then there's no reason to add it to the frontier because you've already visited it. So why would you don't get any benefit by looking at a state again. And furthermore, if it's already in the frontier, there's no reason to again add it to the frontier again, because then there's repeats in the frontier, which is not actually that bad a thing, but it's a waste of resources, it's a waste of memory, it's a waste of time. Okay, so and just quickly, let's just visualize what this looks like. So this is the vacuum world state space diagram, where again we have this robot vacuum that's trying to clean up the room. There's a left and a right side of the room, and let's call the upper left state the initial state. So that is the initial state, and I'm going to circle everything in our frontier in green. So currently, when you initialize the program, you put that one state, the initial state, in the frontier. Okay, and then we go into the inner loop. So now we're going to take an object, take a state out of our frontier data structure, and right now there's only one state, so we take that state, and this is now our current state that we're going to expand. Okay, but before we expand it, we check if it's a goal state. Well, it's not a goal state, so then we move on to the marking step, right? So now we're going to add this state, add this node to the explored set, which I'm indicating by circling it in blue. So anytime I circle something in blue, it's in the explored set. Anything that's circled in green will be in the frontier. Okay, and so now we've marked it that we've already visited this state. Okay, now let's fully expand it. Let's look at all the different actions that are possible from here. Okay, so I've highlighted the different actions. We can move right. We can actually activate the vacuum, or we can move left, which does nothing. So and when we move left, well, we don't actually know that moving left doesn't do anything. So that's a good example to think about, because what happens is then when we go to consider adding that to the frontier, we're going to check, is that in the frontier or is it in the explored set? Well, yes, it's in the explored set, right? It's circled in blue. So what we do is we add the state that we get to by moving right, and we add the state that we get to by activating the suction, but we don't add the state that we're already at because we visited it. We've visited it already. Okay, so this continues. Now this is now our frontier, and let's say we grab the right node. This is now our current state, and we repeat. We again add that to the explored set, marking that we visited it. So we don't want to go back to it. And we look at what are the possible actions from here. Well, we can go left, we can go right, or we can activate the suction. Okay, and if we go left, that state has already been visited. It's circled in blue. If we go right, we're back in the current state, which we've already visited. So that's also in blue. But if we activate the suction, that's a new state. So we should add that to the frontier. So we don't want to add the top row ones, but we want to add the one on the bottom right with the check mark. Okay, and this becomes a new frontier, and this will continue so on and on. So this should give you an idea of, if you run tree search on this naively, you would basically you would allow the search algorithm to go back and forth between, say, the top two states that are currently circled in blue, because you would get, you would always be able to backtrack. So that's a valid move according to tree search. So we should always be aware of graph search versus tree search when we're designing or when we're deciding what search algorithm to run in different environments. Okay, so returning to our review, we also made a very important distinction between different search algorithms in these four aspects of these properties of search algorithms, right? So there's completeness, there's optimality, there's time complexity, and there's space complexity. And we covered a bunch of examples of the search algorithms that we've studied so far. We talked about which ones are complete, which ones are optimal, what the time complexities are of different methods, of different algorithms. And one of the things we had to consider is in these analyses is whether a search space is infinite or finite, right? And that changes whether things are what the different properties of the algorithms are. Okay, and it's worth thinking about at this point, now that I've shown you the difference between tree search and graph search, how these properties change when we switch between tree and graph search. And most of our analysis, a lot of the analysis just carries straight through and it doesn't change at all. But our analysis has been on trees primarily. And one of the examples I gave you is that even in a finite search space, if you run tree search on an environment that has loops that allows you essentially to get back to a previously visited state, then things like depth first search, even if it's finite, aren't, it's not complete because it could go on forever. It could go in that loop forever in the worst case scenario. So it's worth thinking about these things. And then for the different algorithms, here are I just showed some of them on the previous slide, but these are the ones we covered so far. And they basically fit into two families. So there's breadth first family and the depth first family. And in the breadth first family, we have breadth first search, of course, and then we have uniform cost search, which is like a variant on breadth first search. And then we have the depth first search family, where there's depth first search, of course, and then depth limited search, which is like it's just a limited form of depth first search to prevent you from going too far, and then iterative deepening search, which is a depth limited search where you slowly increase that limit. Okay. So with that, we basically finish our review, and it was a review with some extra side information as well. But now let's get on to a new topic, or the new topic of this video. So if you look at these search algorithms, these search algorithms are referred to as uninformed search. Now, why do you think that is? Right? Think about what these algorithms are, and think about why are these uninformed? So the reason that they're called uninformed is because we get to see is the cost of the move right in front of us and the cost we've taken of the steps that we've taken so far. There's no clues from the environment or from experts or any domain knowledge as to what node we should try next. And so as a result, we try something pretty simple, these simple schemes like first in, first out, or even uniform cost is kind of simplistic. I mean, these don't get much information from domain knowledge, right? You can imagine you know a lot about the environment, you know a lot about the search problem, and you basically don't use it with these search algorithms, right? You just all you think about is how hard was it to get to this state and how hard is it going to get to the next state. So instead, just imagine that you know a lot about the search space. In fact, imagine that you know everything there is to know. So again, let's return to the vacuum world example because it's really simple to conceptualize, but at the same time we can see there's a little bit of complexity here. So imagine that you know the entire search space, you know the entire state space and all the transitions and everything, and that's what happens here because we're looking at this diagram. Now you can imagine that the robot has this diagram. If the robot has this diagram, then the story is very different, right? Because we talk about these search algorithms and they're for scenarios where all the AI has access to is what state am I in, what states have I visited previously if it has a memory, and where can I go from here, and maybe what will it cost to get to those other states. But now in this case, we know the entire map, okay, and so running a search algorithm on this, on this map directly with the robot when we already have the map is kind of silly because what you could do instead is just simulate the whole thing, right? You just keep it, this robot vacuum has a CPU in it, so it could just, since it already has the map in its memory, it could just run Dijkstra's algorithm and find the shortest path to any of these the goal states on the bottom. And if we do that, what we get is this. You get this is the shortest path. And then when we go to actually execute the plan, execute the path, it's really easy. We don't have to go to any of these wrong states. We just go immediately, directly in the shortest possible path to a clean state, right? We vacuum, we move right, and then we vacuum again. Okay, and so that's the scenario if we have the entire state space in our memory, or if we know everything, we're completely omniscient. Okay, and occasionally that happens, and you have to watch out for that because you don't want to accidentally use a search algorithm when you could just use a shortest path algorithm. All right, so now let's think about something similar to that scenario, but not quite. So imagine instead of having all of the the whole state space in your memory, we have something else instead. We have we're back in the scenario where we can only see what state we're in, and we can see the states adjacent to us, right? The states that we can get to by taking actions. So these are in green are highlighted. Excuse me, I've highlighted in green the states that we know about, right? We know about the current state that we're in, the initial state. We know about the state that we can get to by moving right. We know about the state we can get to by activating the vacuum. So here's where I'm going to define, something in the environment or something that the AI has access to that's going to buy us almost as much or exactly as much as if we could see the entire state space. So pretend we have an oracle, right? We have some sort of crystal ball or some, I don't know, some person who will tell us something about states that we ask about. Right? We can give the oracle a state and it will tell us something. And what it will tell us is it will tell us the cost to get from any state to a goal state, to the closest goal state or the cheapest goal state. Okay, so in this case, the two states that we're going to be interested in are the state the state where we move to the right and the state that we get to by activating the suction. And the cost, if you count the edges, if you count the number of hops it takes to get to a clean state, a goal state from each of those states, are 3 and 2 respectively. Okay, and so then if we have this oracle, right, this oracle that told us exactly what the cost will be to win the game from these two other states, then we can think about which of these two states do we want to explore first. Okay, and the way we want to make this decision is we want to think about how much will it cost to get to this state, and then how much will it cost to get from that state to a goal. And that's done by this arithmetic, right? So it's going to take one step, right? You have to move right on the top. You have to move right once, and then from there, the oracle is telling you it's going to take 3 more steps to get to the goal state. So 1 + 3 is 4. So that's our score for moving right. Now, for activating the suction on the bottom on the left, we know it's going to cost 1 move to activate the suction, and then the oracle is telling us that it's going to take 2 more moves from there, 2 more actions from there to get to a clean state. So that's 1 + 2 is 3. So that has a better score, right? It's a cheaper score, and so we're going to go there. And you can imagine right away, just looking at the oracle scenario, that this is going to take us directly on that same path that we saw when we imagined having the entire map. Okay, so then let's make things a little bit more complicated. So if you look at the little cartoon of this vacuum world, and this comes from the book, um, let's imagine that things aren't as uniform as we previously drew it, right? There might be extra costs for different moves. Okay, and just for the sake of making this example work, let's look at the wheels here on this robot are on the right side of the vacuum. Um, so maybe for some reason, um, you know if you have to drive the robot from a clean square to a dirty square, that costs more because there's some traction. The traction changes when you change terrain. But if both squares are dirty, then it's easy to roll across from dirt to dirt, right? But if it's clean to dirt, then that costs you something. So then you might have some costs associated with each move, like this right here. So what I've drawn is I've drawn a cost of 1 for any move that is either moving left or moving right across the same type of dirtiness, right? So dirty to dirty or clean to clean. Moving right is just a unit cost, one cost, or it costs 1 unit of whatever work this is. Okay, and then activating the suction costs you 2. Okay, it costs 2 maybe because there's extra energy involved when you turn on the motor for the vacuum. Okay, and so you'll see right here the only sort of special transition is the one I've highlighted, or the one that's now written in larger font, is down there. That's the situation where we move from a clean square to a dirty square, and then again maybe it's because the wheels get caught when the traction changes between the two terrains. Okay, but it's not so important why this would happen. Let's just imagine that's the case. Um, Okay, so let's repeat the same exercise, right? So you start from the initial state on the top right, and these are now the states that we want to consider. And let's actually pretend we're going to use tree search because this actually works if we're even if we do tree search in a graph. So we're not going to check if we've revisited a state previously. We're just going to use the oracle. We're just going to hope that the oracle will help us out. Okay, and we'll be able to remember what moves we've taken so far. So okay, so we're going to ask the oracle. So oracle, how much will it cost to get to a goal state if I take a left loop, right? If I take a left loop from the current state, nothing will happen. I pay one and I basically did nothing. And similarly, what happens if I make a right move, and then what happens if I activate the suction? And the oracle gives us these numbers, which if I did this example out correctly, are correct. And so what do we do with these numbers? Well, we should think about, you know, the combination of two things. Like how much is it going to cost us to get to these different states? And then how much does the oracle tell us it'll cost to get from these states to the solution, to one of the solutions, to one of the goal states? Okay, and so what we get then is these numbers. And then using these numbers, we should decide what state should we explore next. Okay, and again, going back to the search framework, it's what node will we take out of the frontier. Okay, and so what we're going to take, or the node we're going to pick, is the node that's going to cost us, 1 plus 5, right? Because our other options are bigger than that, or are a bigger cost. It's more expensive, according to the oracle. So the oracle's telling us it's going to be cheaper if we try that node. So let's see what happens when we do that. So we take the right, we move right. So I've drawn in red, in these red arrows, the path we've taken so far. And so again, we want to ask the oracle about these three states, right? The one, if what happens if we move left, what happens if we move right, or what happens if we activate the suction. Okay, so the oracle returns these numbers. And so again, we should think about what is it that we want? What's the right decision making process given this information that the oracle told us? And what it is we want to look at, what's the cost to get to that state, and then how much is the oracle telling us it's going to cost to get from that state to a goal. So we have these numbers and according to these numbers, we should try exploring this state that we get to by activating the suction, right? Because according to the oracle, that's going to cost us 2 to get to that state, but then the oracle is telling us it's going to take only 3 more from there. Okay, and then we can continue on. This whole thing repeats again, and we ask the oracle for these numbers, and then we make the decision based on the cost of the total path so far. So at some point, this example actually deviates from what would actually happen in an algorithm, and it's a subtle difference, and we'll deal with it later. But this should give you a good view of how this kind of thinking works, right? So, and here's where we make the final move to cross the finish line, right? So from this state that we're in, the state where the left square is dirty, the right square is clean, and the robot's in the left square. I mean, it's obvious what we should do at this point. But if you just look at the numbers, if you look at the oracle's telling us that if we take the suction move, then we're going to get to a point where it's going to cost us $0 or zero whatever unit is the cost here to get to a goal state, which means we're at a goal state. And again, we make the decision based on what's the total cost of everything, all the moves we've made so far, the move that we're going to make to get to the next state, and the oracle's promise of how much more cost it will take to get to a goal state. Okay, and then finally we get to the clean scenario, and we've won. The robot vacuum can celebrate its victory. Okay, so what we've seen is that getting this oracle information is going to again basically cost us or allow us to take a direct path right to the solution. In this case, it looks a little bit roundabout, but this is the cheapest way to get to the solution, right? Because of that 4 that I put in the left of this diagram. because of that expensive move, it's cheaper to go the roundabout way. And this is getting on the border of something where it's starting to get useful to think about this algorithmically, because there's a lot of information on the screen. I'm sure if you just saw it the first time you saw it, it probably wasn't completely obvious what the cheapest path would be, what the cheapest way to get to the goal would be. So obviously, when we get to real AI problems, it's going to be even more complicated, and so it's something that it's not that easy for a human to do. Humans can do these things, but then we really need algorithms to do these. Okay, so what we did is something very close to the search algorithm that we're going to talk about now, which is the canonical informed search algorithm. It's something that is one of the staples of AI, um, that has been around for decades, but is still one of the most powerful algorithms we've developed so far. So this is something called A star search. So A star search does something very similar to what we did before, which is relying on this oracle. So instead of relying on an oracle, which is impossible. I mean, we don't get oracles in the real world in real AI problems. Otherwise it would be a lot easier to solve these things. What we can do instead is approximate these oracles. We can attempt to design a function or some put some smarts into some way of trying to guess what that oracle value is. And this is where domain knowledge comes into play. This is where you know um, clever modeling of the space, or even learning can come into play. And the way it works is that it's still another search algorithm in our big search framework. So the only special thing here is how do we choose what node to take out of the frontier? How do we choose what state to expand next? And the way we do it is to expand the node with the best evaluation function score, okay, which is defined here, as f of n, where n is the state, and f of n decomposes, or is composed of two things. It's first g of n, which is the cost to get from the initial state to n, and that's something that uh, we can see as an AI algorithm. We get that information because we basically have measured it ourselves as we've taken these paths from the initial state to the current state. And then the second piece is h of n, is the heuristic estimate of the cost to get from n to the goal. Okay, and if this is not an estimate, if this is the true cost, then we are talking about that oracle I just showed you, right? And if it's the oracle, then what we've seen, at least from a single example, is that we're going to do really, really well. We're going to basically be able to do this in the most omniscient, perfect way that is possible. But again, in real AI problems, we won't have an oracle. So then the question or the problem posed to us as AI researchers or designers or engineers is to come up with heuristic functions that approximate this oracle, but at the same time behave well theoretically. And so we're going to think about how these heuristic functions affect the properties of A star search, the completeness of it, the optimality, and the time and space complexity. And so we'll go over these and look at different examples of heuristic functions, um, and how they affect these properties in class, and then we'll think more about how to design good heuristics. And to get you started, I want you to think about one question first. So looking at this definition of A star search and thinking about how we sort of watched it work in the example, um, what is a heuristic function here that will guarantee completeness? And a hint is it's a heuristic function that will turn A star search into another form of search that we've already looked at. Okay, so let's talk about that next class.